Brussels, 1927. 29 of the world's most brilliant minds gather for the Solvay Conference. Among them are Nobel laureates, pioneers of the atom, and the architects of the nuclear age. But beneath the polite exterior of a scientific summit, a war is being waged. It is not a war of weapons, but of ideas, a battle for the very soul of reality. On one side stands Albert Einstein, the man who mastered the cosmos. On the other, Niels Bohr, the man who peered into the heart of the atom. Einstein believes the universe is orderly, predictable, and governed by strict laws. Bohr argues that at its most fundamental level, the world is a chaotic game of chance where nothing is certain until it is observed. If Bohr is right, everything we thought we knew about existence is an illusion. If Einstein is right, the new physics is a house of cards. The stakes are nothing less than the definition of truth itself. To understand this rivalry, we must look at the world they had already built. By the early 1900s, physics was considered a nearly finished book. Sir Isaac Newton had provided the laws of motion. James Clerk Maxwell had explained light and electromagnetism. The universe was a giant clock ticking away with mathematical precision. Albert Einstein had revolutionized this clock with his theory of relativity. He showed that space and time were flexible, yet they still followed rigid causal rules. In Einstein's universe, if you knew the position and velocity of every particle, you could predict the future with absolute certainty. But as scientists began to look closer at the subatomic level, the clock began to break. Niels Bohr, working in Copenhagen, was uncovering a world that defied logic. In this quantum realm, particles like electrons didn't behave like tiny billiard balls. They existed in multiple places at once. They vanished and reappeared. Most disturbingly, they seemed to change their behavior simply because someone was looking at them. Bohr embraced this weirdness. He proposed that reality was not a fixed thing, but a series of probabilities. Einstein could not accept this. To him, science was about discovering an objective reality that existed whether we looked at it or not. He famously muttered his protest, "God does not play dice with the universe." Bohr's response was just as sharp. Einstein, stop telling God what to do. The conflict reached its boiling point in the dining halls of Brussels. Every morning at breakfast, Einstein would arrive with a new thought experiment, a complex riddle designed to prove that quantum mechanics was logically inconsistent. He would use mirrors, shutters, and moving clocks to try and trap the quantum world in a contradiction. Bohr would sit in silence, listening intently, his face clouded with worry. He would spend the rest of the day pacing the streets, muttering to himself, searching for a flaw in Einstein's logic. Then, every evening at dinner, Bohr would return with a solution. One by one, he dismantled Einstein's traps. The most famous of these encounters involved a box filled with light. Einstein argued that by weighing the box before and after a single photon escaped, one could measure both the time of the escape and the energy of the light with perfect precision. This would violate the Heisenberg uncertainty principle, the cornerstone of Bohr's theory. Bohr was devastated. He spent a sleepless night in a state of near panic. But by dawn, he had found the answer. In a twist of irony, Bohr used Einstein's own theory of general relativity to defeat him. He showed that the very act of weighing the box in a gravitational field would blur the time measurement just enough to satisfy the uncertainty principle. Einstein had been beaten by his own greatest discovery. As the years passed, the debate shifted from the dinner table to the academic journals. Einstein, now living in exile in Princeton, refused to give up. In 1935, he released what he believed was the final blow, the EPR paper, named after himself and his colleagues, Podolsky and Rosen. He described a phenomenon we now call quantum entanglement. If two particles are created together, they remain linked. If you change the state of one, the other changes instantly, even if it is on the other side of the galaxy. Einstein called this spooky action at a distance. He argued that since nothing can travel faster than light, the particles must have had hidden variables, internal instructions, from the very beginning. He believed Bohr's theory was incomplete because it couldn't explain these hidden rules. Bohr's rebuttal was philosophical. He argued that the two particles were not two separate things at all, but a single system that remained one regardless of the distance between them. For the rest of their lives, neither man would budge. They remained close friends, admiring each other's genius, but they inhabited two different realities.